Hey there, in this video we're going to continue our discussion of average velocity and instantaneous velocity. So the prior video I asked you to do this on your own, and so hopefully by now you have completed it. And let's go over it. I'll just really quickly type up what the answers are, or write out what the answers are, and then you can see what you did. So if you call this, well, this is t, and if you call this f of t, right? So then you have on the interval 36 to 42, if you have AB, last time we discussed in the last video, the average velocity is f of b minus f of a over b minus a. So in this case, if our interval AB is the interval 36 to 42. So you will be doing f of 42 minus f of 36 all over 42 minus 36. And so you will look at f of 42, so the heartbeats when the time is 42, so 29:48 minus the heartbeats when we are at 36, so 25:30 all over then 42 minus 36. And when you do this calculation, you should get 69.67. And the units will be beats or heartbeats per minute. We look at our units here, heartbeats per minute. So beats per minute. And so 69.67 is the one for the first interval. Now in this interval, this is 38 to 42. So I'm going to skip the math in here and just say the answer was 71.75 beats per minute. And so that hopefully is what you got. For the interval 40 to 42, what did we get? So on 40 to 42, I got 71 exactly. So 71 beats per minute. So let's see what's happening. 69.67, 71.75, 71. So it's looking pretty close, those values. So what happens on the last one? On the interval 42 to 44. Here the average velocity ends up being, so the average rate of change is 66 beats per minute. All right, so 69.67, I hope you can see my point there. 69.67, 71.75, 71, and then 66. So what are your conclusions about this patient? So, right, we're looking for the slope of the line, which represents the rate of change, in this case, of the heartbeats after t minutes. So, it looks like, I will say, the person was pretty stable, and then the heartbeat dropped after 42 minutes. Because notice that between 36 to 42, the answers are, the average rate of change is pretty close to each other. So that means that the heart rate, right, is pretty stable. But then between 42, after 42 minutes, it dropped. So then we can say that from the data, we see that the patient's heart rate is decreasing from 71 beats per minute to 66 heartbeats per minute after 42 minutes. And so we can say after being stable, the patient's heart rate is dropping based on the data. Okay. So this was mostly an example of how you can use average rate of change to make conclusions about data. All right, so back to our discussion about tangent lines and secant lines. I'll just give you a general idea of what the slope of the tangent line and the slope of the secant line mean. So say I have a general graph such as this one. And so we have here is our y-axis and our x-axis, and let's look at an interval from A to B. So if I'm looking on the interval from A to B, then this is f of A, and somewhere over here I have f of B. And so this, when I connect the dots here, between A and B, f of A and f of B. Let me make it red instead. Okay, so that we can see it better. And so this, because it's a line that's connecting 2 points, this is my secant line. And what is the slope? The slope of any line, so let me just go here. The slope of any line is y2 minus y1 over x2 minus x1, right? The change in y over the change in x. Average velocity, change in position over the change in time. So our slope here for the secant line would be change in y, so f of b minus f of a over b minus a. And as if I start moving this a little closer, so say I have then a and a plus h. I'm actually going to call it x and x plus h. And let me redo the graph. So changing my a and my b to x and x plus h, I have noticed that I have the same line, right? But now here, this x gives me f of x, and x plus h, because this is the function f of x, gives me f of x plus h. And so the slope of the secant line, just as we did before, would be the change in y over the change in x. So here we had f of b minus f of a over b minus a. All I did was change the a and the b to x and x plus h. And so this is going to be the slope of the secant line, f of x plus h minus f of x all over x plus h minus x, right? F of b minus f of a over b minus h. And this is how we get our difference quotient. So f of x plus h minus f of x all over h. So the difference quotient represents the slope of a secant line connecting the value of x, so f of x, and the value of x plus h, f of x plus h. And the reason I change it from a, b to x and x plus h is that I want to calculate the instantaneous velocity. So I want this h to get really small. How small? Really small, close to zero. Right? So we want to move this h closer and closer to x so we can calculate the instantaneous velocity at x. So the smaller that h gets, so then, like for example, if h is 1, then this is x and then x plus 1. If h is 0.1, then now this is 1 and 1 plus 0.1, or x and x plus 0.1, right? So it gets smaller. So I want to bring this h closer. And so I'm going to draw a different tangent line. And then as h gets smaller and smaller and smaller, the idea is that as h gets really, 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 really small, right? How small? Close to zero small. Then I'm going to have just a tangent line, a line that touches the graph at exactly 1 point, and that's going to be at the point x. So that green line, my graph is not the best. In your textbook, there should be a graph illustrating this as well. That might make it a little bit clearer. I'm going to see if I can copy that graph onto here. So here you have the slope of your tangent line. So what is the slope of the tangent line then? If you don't have 2 points, so the slope of our tangent line is as h gets really, really small, right? So then the slope of the tangent line at x will be essentially f of x plus h still minus f of x all over h as h gets really small. How small? We can say as h goes to 0. And this is where the idea of a limit is going to come in. So we can say that the slope of the secant line, the tangent line, will be the limit as h goes to 0, right? As h gets really, really small of the difference quotient. And this has a special name And we'll talk about that in the next section. Here's a slightly better graph than my hand-drawn one, and so this will be very similar. So if this is my x, and then say I start with my x plus h here, right, then this line represents the secant line. And then if I move the h, right, h is getting smaller. So then if x plus h is now over here, now that's the secant line. And then h keeps getting smaller. So now this is x plus h. And that is the secant line until h gets really, really close to 0, to where the x and x plus h are almost indistinguishable. Then that, the red line here, is your tangent line. Let's try an example. So find an expression for the instantaneous rate of change at x equals 2 of a particle that moves on that path. So instantaneous rate of change, so that is essentially we're looking for the slope of the tangent line. So the tangent line, the slope of this line is the essentially instantaneous rate of change. Whereas when you have a secant line, the slope of a secant line is the average rate of change or average velocity. Right, so here we'll find an expression for the instantaneous rate of change at x equals 2. So the instantaneous rate of change, then I want the slope of the tangent line. And as we talked about here, the slope of the tangent line is, as h gets really small, the difference quotient. So I will say, as h gets small, since we haven't talked about limit notation yet, as h gets small, the slope, the instantaneous rate of change, is f of x plus h minus f of x over h. So because I want to find it at x equals 2, this will be then f of 2 plus h minus f of 2 all over h. And so we simplify this. So what is f of 2 plus h? So look at our function, is x squared minus 2x plus 1. X is 2. So, well, we're going to plug in 2 plus h. So this, I'm going to have 2 plus h squared minus 2 times 2 plus h, right? Everywhere you see an x, plug in 2 plus h. And plus 1 over here. So 2 plus h quantity squared minus 2 times 2 plus h plus 1. And simplify what this is. So f of 2 plus h. So I know that x is 2, but we already plugged it into the 1 here. So we already said x equals 2 there, which gave us this. So now this is what we're simplifying. And now we look at the function, and I need to find f of 2 plus h. So then I plug 2 plus h into there. So I don't plug in 2 anymore because I already did it here. So what is this? Multiply it out. So it'll be 4 plus 2h, 2 of those, so plus 4h plus h squared. Distribute the minus 2. Don't forget to take the negative with you. So minus 4 minus 2h and then plus 1. And if you want to simplify it here, go ahead and combine like terms. So I guess I could get rid of this parentheses, but notice that 4 minus 4, so those end up canceling. I have 4h and minus 2h, so that's going to give us what? So I'm going to have 2h, right? 4h minus 2h plus h squared plus 1. You could write it in descending order, so h squared plus 2h plus 1. So this is our f of 2 plus h. What about f of 2? F of 2, now we plug it into just x here, because it's just f of 2. So I replaced the 2 for x. Here I was finding f of 2 plus h, so I take the whole 2 plus h and replace it in x. So this will be 2 squared minus 2 times 2 plus 1, which is just 1. So putting it together, f of x plus h minus f of x over h, in our case, is f of 2 plus h minus f of 2 over h. And so we can say, well, f of 2 plus h is this thing, h squared plus 2h plus 1. So let's play it in. So h squared plus 2h plus 1 minus f of 2. F of 2 is 1, so we're going to plug in 1 in there, all over h. And 1 minus 1 is 0, so those go away, and what are we left with? So we're left with h squared plus 2h over h, and we can factor out that h from the numerator. And now I can divide those out. H divided by h is 1, and so we're left with our rate of change is h plus 2. Now we did say that the instantaneous rate of change is this as h gets small, as h goes to 0, meaning h gets small. So what happens as h gets small, close to 0? We're just going to get 2. So we can say that our instantaneous rate of change is 2. Cool. Email me if you have any questions. And so this is where being comfortable on simplifying the difference quotient is going to be huge in this class. This is the beginning. We're going to continue that this difference quotient is going to continue to come up and continue to come up. So I'm going to want you to be really comfortable with this. So try the problems on the homework, try extra problems if you need. Email me if you want extra difference quotient problems just to practice.